The planet's Great Red Spot is the biggest storm in the solar system. It used to be much larger than it is now. Its sheer profundity is difficult to comprehend. To put it in perspective, imagine about 45 Mariana Trenches piled on top of one another on Earth. Hurricanes weaken rapidly over land, but since Jupiter is a barren planet, there is no friction to weaken the enormous storm. Although it has been raging for centuries, the Great Red Spot appears to be experiencing an unusual development. It has decreased dramatically since the late 19th century, changing in size, shape, and even color. Hello, and welcome to Z. The Great Red Spot storm is now around 10,000 miles wide, but it was once a huge oval 3 times wider than Earth. Over time, it has become more circular in shape. Its tints have varied from light to bright reddish-orange. Though the precise mechanisms are yet unknown, scientists think that substances like ammonia and hydrocarbons in Jupiter's upper layers may be responsible for these colors. The Great Red Spot is just one amazing feature of the gas giant Jupiter. The atmosphere of Jupiter is a whirling jumble of belts, zones, and cyclones, with powerful winds blowing from east to west between the characteristic bands of clouds. Although it barely accounts for 1% of the planet's mass, it is incredibly complex, and the mechanisms underlying its unusual characteristics are still unclear. The jet streams, or comparatively steady winds, of the massive gas planet are well known. Some of them stretch more than 1,850 miles below the planet's clouds, are more than 3,000 miles broad, and can reach speeds of 320 miles per hour. Looking at Jupiter and Earth side by side, it appears that they are 2 completely distinct planets. Surprisingly, though, there is a connection between the 2 worlds. When researchers examined the constituents of Jupiter's atmosphere, they found a surprising distribution of ammonia in large amounts. There are even ammonia columns that reach up to Jupiter's upper cloud layers and extend deep within the planet, but concentrations are significantly higher in some areas. Scientists discovered that a vertical flow is produced by the interaction between Jupiter's upper and lower atmospheric layers, a phenomenon that also occurs on Earth, using data from NASA's Juno satellite. There are 2 types of wind patterns on Earth called ferrule cells. Near the equator of our world are regions known as Hadley cells, which force warm air upward toward the poles. The ferrule cells function as a buffer zone between the polar cells, which drive cold air downward. They rotate in the opposite direction from neighboring cells, causing the wind to flow through each hemisphere in a zigzag pattern. However, there are 8 of these patterns on the solar system's largest planet. Scientists believe that this is the process by which Jupiter's recognizable color bands form, since these cells line up with the expected borders of what we may refer to as Jupiter's equivalent of Earth's ferrule cells. The absence of a solid surface on Jupiter is the primary reason for the differences in wind patterns between Earth and the gas giant. However, a few miles below the gas giant cloud, scientists believe they have discovered something intriguing that may function as a stable layer akin to the surface of Earth. Computer models indicate that there appears to be a cause slowing down Jupiter's winds in circular patterns. One theory is the possibility of extremely tall vertical ferrule cells similar to those on Earth. These cells may be influencing the direction of the winds and producing oddities such as ammonia accumulating into slushy oval forms that reach 60 miles into Jupiter's atmosphere. Ammonia rises and becomes colder, forming icy clouds in the upper atmosphere. Subsequently, the remaining air descends again, but its ammonia content decreases, resulting in a sort of column where ammonia concentration increases from the bottom to the top. Lightning is likewise caused by an ammonia-water mix, and it primarily occurs close to the planet's poles. The enormous atmosphere of Jupiter is then swept by violent thunderstorms. Strong Jovian storms have the potential to produce strange hailstones called mushballs, which are high in ammonia. It is thought that water ice crystals are lifted by thunderstorms to heights of more than 16 miles above water clouds, which is how mushballs on Jupiter occur. They come into ammonia vapor there, which melts the ice and creates a peculiar ammonia and water combination. As a result of ammonia's antifreeze properties, liquid droplets can develop inside these freshly created clouds even at temperatures below -16 degrees Fahrenheit, where liquid water cannot exist. Lightning can be produced when ammonia-water liquid droplets contact rising water ice crystals, electrifying the clouds. The mushballs get heavier as they get bigger because they accumulate layers of ice and slush. They eventually become too big and sink further into Jupiter's atmosphere. There, they evaporate because of the warmer weather. All of this demonstrates how much more intricate Jupiter's atmosphere is than what we had previously thought. The Great Red Spot, Jupiter's model bands, and its areas of light and dark have all been investigated by astronomers in the past. However, our understanding of the giant's interior dynamics beneath its atmospheric layer is surprisingly limited. Gas giant planets most likely feature a gradual transition from the atmosphere to the planetary core rather than distinct inner layers similar to those found on Earth-like planets. Let's say that you collided with Jupiter. As you move further into the planet's clouds, what would you see and experience? First of all, since it is a gas giant, you would fall farther and farther without coming to rest on a solid surface. However, the free fall would seem endless, even if it wouldn't last that long before you died. Severe radiation would seep through your suit even before you approach Jupiter, resulting in your instant demise. You would therefore require a highly developed radiation-proof spacesuit to give yourself some chance of surviving in this harsh environment. Free-falling particles accelerate by approximately 32 feet per second every second on our planet. Your free-falling speed, often referred to as terminal velocity, would be roughly 2,000 miles per hour as you descended to the top of Jupiter's atmosphere, much faster than a fighter jet using its full afterburners. You would eventually pass through the ammonia cloud zone, where the temperature drops to an extremely cold -240 degrees Fahrenheit. If you were in Jupiter's clouds, you would be tossed around like a leaf in a tornado due to the tremendous winds that may reach up to 425 miles per hour. Furthermore, the upper atmosphere of the gas giant spins at 110,000 miles per hour, meaning that a collision with a dense gas cloud would be like hitting a wall at this speed. If you made it beyond the earlier challenges, you should see colored clouds changing as you descend. Ammonium hydrosulfide and ammonium sulfide are present in these clouds. Their color is rather brown, and the farther you descend, the more brown it gets. Even without a spacesuit, the pressure surrounding you would initially be tolerable, about the same as what it would be like to be 100 feet below the surface of the Earth. That pressure would eventually increase to 1,000 times that of the Earth's atmosphere. The physiological effects of breathing gases at high pressures cannot be avoided, even though a spacesuit can shield you from outward pressure. Because of nitrogen narcosis and oxygen toxicity, inhaling regular air at 10 times the Earth's pressure is exceedingly risky. When the body is exposed to high oxygen concentrations for an extended length of time, oxygen poisoning develops. Inhaling air with high oxygen concentrations at high pressures can cause the body to produce reactive oxygen species, which can harm tissues and cells. This may have fatal results and cause symptoms ranging from slight pain to convulsions. When nitrogen gas dissolves in the bloodstream under high pressure, it can cause nitrogen narcosis, which has effects on brain function akin to those of sedatives or alcohol. Nitrogen narcosis can lead to more severe symptoms such as confusion, hallucinations, or loss of consciousness, but it can also bring euphoria, altered perception, and impaired judgment. The solubility of gases in the bloodstream is impacted by pressure, which has an impact on both nitrogen narcosis and oxygen toxicity. The amount of nitrogen and oxygen dissolved in the blood increases along with pressure. In order to prevent this, your spacesuit would need to add helium or neon to the air mixture in order to maintain safe levels of nitrogen and oxygen. And your protracted descent toward Jupiter is only getting started. Because of the increased pressure, it grows darker as you descend farther and farther. Because light cannot easily get through the thick and opaque atmosphere of a gas giant, visibility would be restricted. The atmosphere becomes foggy and murky as light enters because it is absorbed and scattered by the thick gases and particles. It would be tough to see more than a few feet away, even with a bright light source installed in your spacesuit. As a result, you'll require specialized tools and equipment with sensors that can monitor your surroundings. You would enter an area of the massive gas giant that has never been investigated before if you could somehow withstand the extreme pressures more than 400 miles below Jupiter's atmosphere. Jupiter's thick atmosphere would absorb all radio transmissions, meaning there would be no way to communicate with Earth or even a neighboring satellite. It would take more than 20 hours to reach the gas giant's center, but halfway there, you would be in temperatures high enough to melt tungsten, a grayish-white metal that has the highest melting point of any metal known to science. You can't possibly survive this because the pressure is increasing rapidly the entire time. Your free fall would be slowed down by the increased pressure, which would also work against your downward motion. It's like trying to get around in thick syrup or mud. It becomes more difficult to move fast through denser materials. Therefore, even though gravity is pushing you downward, your descent is progressively slowed down by Jupiter's atmosphere's growing density. When your body eventually reaches Jupiter's core, which is believed to be made of metallic hydrogen, it has been traveling for almost 10 hours. There, the pressure reaches roughly 2 million Earth atmospheres, and the temperatures are higher than that of the Sun's surface. Because of how thick the atmosphere is, metallic hydrogen becomes liquid. In conditions similar to the inside of Jupiter, where oxygen is scarce or non-existent, your body would experience a phenomenon known as carbonization. The organic matter in the body undergoes a chemical transformation in the absence of oxygen, which is necessary for the regular processes of decay or decomposition. It is characterized by high temperatures and the breakdown of organic substances producing residues that are rich in carbon, much like charcoal. A force equivalent to almost 650 million pounds would be applied to every square inch of your body, or the bit of charcoal it has become, due to the extreme pressure. But let's say your physical form doesn't change. It is mostly made up of water, and because water molecules have strong hydrogen bonds, they are resistant to outside forces that would otherwise bring them closer together. Because of this, water is nearly incompressible and maintains most of its volume and density even at very high pressures. Your body's density would eventually coincide with that of the environment. You no longer fall. Instead, your body floats in midair. Thank you.